continue on solving the crystal structure. So before the break, we focused on how to calculate Q values of the diffraction peaks from the reciprocal lattice. So now I'd like to show you the relation between the crystal periodic lines and the diffraction peaks. It's a much more a real space relation. That's actually what I did most when I was a graduate student. I didn't really do much, if at all, the Miller indices. So wasn't a, so you guys are ahead of me if you're a student. I didn't learn that until much later. So first, now let's review the Bragg's law for a 2D crystals. The diffraction results from the interference of the X-ray scattering off periodical lines here. So in 3D, you hear probably people saying crystal planes. So 2Ds are lines. So then when the path lines difference between the incident and scattered beam line, beams, X-ray beams satisfy this Bragg's law, in which n is the integer, lambda is the wavelength X-rays, and d is the spacing here, and the theta is the angle between the beam and the plane. You will see a diffraction peak at that direction. Each of these diffractions we've labeled here, if you got to label a few, corresponding to a d spacing here in the real lattice. And that's what I like to find out just by drawing lines of those d spacings. Okay, so the first one's called nearest neighbor spacings. We find a center and then the next nearest neighbors spots here. So all I need to do is just draw lines at the connecting all the nearest neighbors. And that gives you 3D spacings. And we have said that we asked you the degeneracy of this peak, and this corresponding to all the 3 spacings but 6-fold symmetry, because this rotated 180 degrees is another symmetry. So all of those landed in the same peak. So this degeneracy is 6. And that's because we have polycrystals. If I have a single crystals, you shine a line, you get 6 spots. Okay, so that gives you the d spacing and the first peak corresponding to the 2 pi over d. That's the first order peak. The second order peak is the next nearest neighbor. So you draw lines connecting all the next nearest neighbors. You get all the lines, and you got the d spacing here. I didn't draw here, but that's a shorter d spacing, d over square root of 3. Just pure geometry, you can figure that out. So the q, because it's inverse relationship, q is larger. So the second order peak is here. And that's again, I remind you, the inverse relationship. It's the smaller the spacing, the larger q value is. The higher order it is, the smaller the d spacing it is. So the third order, now third order is a little peculiar. It doesn't cross any dots. It's halfway between this nearest neighbor lines. I'll get back to that later. And the fourth one is the next nearest neighbor. So again, you just draw lines connecting those dots, and so on and so forth. And just by connecting dots, you'll be able to find the highlight. It's cumbersome, but if you prefer the real space, and that's what I did a lot of time in grad school, that's how I got the d spacings from here instead of a cube space. Okay, so I wanted to get back to this line here. Why it doesn't cross any of the dots here? Well, that's because of this end here. Okay, the Bragg's law has an n lambda equals 2d spacing. So for each d spacing, this d is just this particular d, but that could mean any other d. For any of the d spacings, that could be many, many, many peaks, and correspond to 1 and 2 and 3. So n equals 1 is this d, n equals 2 is half of the d spacing. Okay. So in fact, this is actually much easier to view in the reciprocal lattice space, this presentation. So if you follow the same directions, all those spots lining up, they belong to the same harmonic group. So the first one, n equals to 1, that's a first order. And then the third order is twice of this, n equals 2, fifth, and the eighth. They're all here. Okay, that same color belongs to indicating what the order the peaks are. You get a solution like that, so it marks all the orders for the assignment, number 1. So the second order peak, the higher order in this limited the circles or dots, that's the 6th one. And that's the 6th order peak. You can count it 1, 2, 3, 4, 5, 6. I think there's 7 peaks around here. So that's how they related. So that I find is pretty neat. You can find the higher orders in addition to all the diffraction lines crossing dots. Okay, so now we'll look at the structure for the lipid monolayers after the monolayer for lipid DPPC lipids, for example. So first, we're just assuming they're standing straight. And when you're standing straight, you have a perfect hexagon, and the diffraction peak should be just one in-plane peak. However, if you tilt it, or we already mentioned that if you tilted the beam, a peak will split into 2. And by connecting the lines, we've done that before, you'll find out the direction that not along the tilt will remain the same. And that's this 2 pi over d3, this particular one that didn't change. However, the other 2 direction, d1, d2, which is equal, they are stretched. They're becoming larger spacing. And the larger spacing means a smaller Q value. Not only that, but also it form an outplane peak. And this outplane peak is much easier to illustrate in our beloved reciprocal space. That's what we're going to do next. Okay, so in the real space, we're already familiar with this skinny cylinder representation of the monolayers. In the reciprocal space, this blue hexagon is what we have done. We'll give you the hexagon for your homework. It's just the first 6 spots here. And you look at it, it's a little distorted, but it's not distorted. It's ways a heroic effort to make it like 3D. So we can plot the 2D structure factor, which is the blue plane represented, and this Bragg rods that's along the QZ direction, but at the all the first order peaks, okay, for this standing straight illustration. So these are blacks are Bragg rods, it's infinite tall, and this pink disk here represents the form factor of a cylinder. Remember, we already mentioned we use a oblate ellipsoid to represent this disk. It's hard to draw, so we use this pink disk to represent this form factor. So in this representation, the maxima of the peak along the Bragg rod is where the pink disk intersects those rods. Okay, so with that, we're ready to describe the tilt faces. So we define the angle of tilt as the long axis of the lipid relative to the normal, call it theta t. So in the hexagonal non-tilted case, theta t equals 0. So in here, the pink is coincide with the blue plane. These two planes coincide to each other. They're all flat. And so the pink disk cuts the Bragg rod at the horizontal. And you see one peak. That was because it's a 6-fold symmetry and give you all 6 spots at the same place. And the reason you only see half the peak is because the other half is under the blue plane. So anything under the blue plane, meaning under the water, you can't see it. So you got the half of that. So the second example is a distorted, but still not tilted. So theta t now still 0, but this thing is squashed. And that split the peaks. We already said it. Anything distorted, not symmetric, and you have 2 peaks, and they're both in plane, peaked at the qz equals 0. And you have now 4 1-1 peaks. All those 1-1 peaks are the same, give you the same value, qxy value, and the 2 0-2s give you another value. So that's why the intensity is 2-to-1. Again, they're half buried in the water. Now we get to the tilt. So the first tilt is along nearest neighbor. Okay, so that means the pink disk is tilted. So if I use my 2 hands, I still enough hands to illustrate that. The blue is my left hand, and they stay the same, but the pink tilted to that direction because the molecule tilted this way. So the pink is cutting the Bragg rod on the left-hand side at the bottom below the blue plane, the 2 peaks here, and cuts the Bragg rods above the blue plane, so on top here. And the other 2 along the non-tilted direction remains the same. So you have this 2 peaks remain the same on the plane, but this 1-1 peak, there are only 2 1-1 peaks here. The other 2 you can't see. So that's why the intensity is the same, except that this one only you see half. Now we get to the tilt along next nearest neighbor along this axis. And this tilt, it tilts along this axis. So this is the blue, and this pink's going like this. Now you see all 6 peaks are out of plane. 3 below the blue in front of you, and 3 above the blue. This is above the water. So they're all out of plane. So, however, I will leave you to figure out the intensity ratio, why there's a 2-to-1 and why O2 now is on the other side. So I'll leave you to figure that out. So this configuration, this illustration is referenced from Weibu's thesis and one of Mark Schlossman's papers. So after you solve the structure of the monolayers that you measured, and you were able to use these equations listed here, and this is again from Wei's thesis, to obtain the tilted angle and the area per molecules. A lot of people are interested in that. So you get the peak positions, you get all the other things from your diffraction peaks. And that's part of your second assignment. So now, well, the heavy lifting part of the lecture is over. The next 2 subjects are relatively shorter. So first, let's see how we determine the correlation length of the structure from the width of the Bragg peaks. So what is the correlation length of a crystal? I checked, and there are many more definitions, but for us, we use it here to describe the domain size of a crystal within which the particles are scattered coherently. So in other words, it's the size of a perfect crystal. So I use 1D array of the dots to illustrate the relation. And this 1D array of dots behaves just like a 1D grading, 1D diffraction grading you're probably familiar with. And this diffraction pattern of a 1D grading can be described with this simple function here. We ignored the form factor that of this envelope actually is a form factor from single slits, which is considered this infinite narrow. So it's become a constant, it doesn't modulate the intensity anymore. So the functional form, the diffraction patterns plot as a function of the coherent length, which is proportional to n, is plotted here. And you can see that the width of the main peak here is inverse proportional to the coherent length, and the intensity is proportional to the n squared. Remember in the first part of the lecture, I mentioned that when you break out the 2D crystal, perfect crystal into little pieces, you see the peak width broadening, and that's the reason. Okay, so we can see with a real example how to determine the correlating length of your sample. Again, this is from the gold nanoparticle monolayers, and you can do that with any diffraction from your sample, any kind of samples if you wanted to do. So this is just the intensity integrated over Z, plotted at QXY intensity here. So we can estimate the average correlation length. It's not exact, it's the average correlation length use the width of the first order peak because it's a stronger. So two factors contribute to this measured peak width. We call it measured peak width. One is attributed to the average domain size, and that peak width called dQXY, it's intrinsic peak width. And the other is attributed from the instrumental broadening called resolution function. That's because the slit size you put in front of the detector and the distance between your sample to the detector. So the three peak widths are related by this equation. So how do we obtain this intrinsic peak width? Well, you first fit the correlation length now is just inverse proportional to the delta QXY in this equation. So to obtain this measured peak, and you fit with a Gaussian, it doesn't have to be a Gaussian, it could be a Lorentzian, or you can go fancier, it could be the convolution Lorentzian with Gaussian. I think that's a void function. I think Kathleen will be familiar with, and she spent a lot of time using that fancy function to fit her peaks. So with that fitting, this is just simple Gaussian with background, and you get the measured peak width at 0.012 unstrung inverse. In the resolution function, this geometries give you a good approximation for the angular resolution, but it's not exact. So the exact calculation, it's too complicated. Honestly, I don't even know. So I was given this number, put it here, 0.01 unstrung inverse. And now using this equation, we get the intrinsic peak width, that is 0.007. So you substitute that into this equation, you get about 10 gold nanoparticles. That's the island size, the domain size. Or to point out, the measured peak width will never be less than resolution function. So if you find out your peak width is about the same as the resolution function, you know your measurement is resolution limited, and you need to go find way to somehow improve the resolutions. And typically, you move the detector further away from the samples if you cannot tighten this slit anymore. And that's why you see this detector arrangement in small angle, and they're far away, sometimes 10, 20, 25 meters away to increase their resolution. Okay, so the last part of the talk is about determining the shape of the particles from diffraction pattern. So recall that we defined the form factor that is the Fourier transform of the electron density function of individual particles. So for a uniform spheres with a radius r, then the electron density function is 1 over v, and v is the volume of this spheres. And you carry out the integration, you get this quite simple expression. Note that it's a function of q, so it's symmetric. So if you plot it on just qz direction, it looks like this, but it's symmetric. As I said, it's more like a spheres if you take the first part of the minimum. So for a cylinder, a uniform cylinder with radius r and length L oriented along z directions, the form factor along the z direction doesn't depend on r. It's just the sync function with the length in there. The form factor actually along qxy, I already mentioned, is the Bessel function. So it's like a disk. Okay, I should mention first that this form factor along qz direction is also oscillating. It's a simple sync function. If you have a rod that's tilted, okay, so this tilted means that you have this oblated ellipsoid tilted, then the form factor along the QZ is no longer perfect sync, but has a component of Bessel function. And that's very complicated. It's still a combination. The form factor is still a combination of the Bessel function and the sync function, but with tilt angle buried in there. But most of the time, because the tilt is small, we were just using this sync function to fit our data. And that's good enough because you're just getting the length and you're not getting exact the length, just approximate. Okay, so let's look at the data for the gold nanoparticles. Again, we wanted to fit the Bragg rod, meaning I'll just cut the data vertically and take that and plot it into a function for QZ here. So that's the intensity, and the function looks like this. The blue symbols here are the data, and the red line here is the fit of this form factor of sphere convoluted with the particle distribution function. And the reason they have to convolute with this is because your nanoparticle sphere has a size distribution. They're not perfectly the same. That best one is like 5 to 10%. The worst one could be anywhere you can imagine. So immediately you probably notice one thing, that this polydispersity smear out the very sharp drop of the minimums here we drew before. And there are other factors that smear out in the instrumentation resolution functions or noise, what have you. So that's and from this fitting, you can get the size of R here. And for the lipid, you get your data this way, cut it vertically this way. And we don't see that many minimums here because it's not because it's not there. It's because the data is just not, the scattering is not very strong. And here we fit this vertical data with this rods, just simple sync function, assuming it's not tilted. And it gets a very good fit here. So with that, we conclude the lecture on GID. Now let's just quickly summarize what we have covered. First, we examined the functional relationships between the real space, electron density distribution of the sample, and the reciprocal space, structure factor and form factor. And we then look at a few examples to get the conceptual idea how to relate the diffraction pattern with the structure of your sample. Following that, we work on how to build a reciprocal lattice from a real lattice to index the diffraction peaks with Miller indices and solve the crystal structure. And we also worked on how to understand the diffraction patterns from monolayers that tilted in a reciprocal space. And after that, we work on how to determine the correlation length of the structure from fitting the diffraction peak and with the information resolution function. And finally, we saw the functional form of the form factors for a sphere and the cylinders and how to use them to obtain the shape of the particles or the size of particle from diffraction peak. And that's all for the